Right now, a signal from Voyager 1 takes nearly 23 and a half hours to reach Earth. And by the time it arrives, the probe has already traveled another 1.4 million kilometers deeper into interstellar space. These two spacecraft didn't just go farther than anything humanity has ever built. They kept finding things nobody predicted along the way, and they're still rewriting what we thought we knew about our cosmic neighborhood. Before the probes ever reached interstellar space, before the signal delays stretched to nearly a full day, they had to run a gauntlet of 4 giant planets. And what they found at each one didn't just add to the map, it kept tearing it up and redrawing it from scratch. Jupiter was the first stop and the first shock. The discovery of active volcanism on Io was the greatest unexpected find at Jupiter. The first time active volcanoes had been confirmed on any body in the solar system beyond Earth. Up until that point, scientists assumed geological activity at that scale required a planet-sized body with a hot interior. Io is a moon, and it was erupting. Plumes from those volcanoes extended more than 300 kilometers above the surface. The mechanism turned out to be gravitational. Jupiter and its neighboring moons are essentially kneading Io like dough, generating enough internal heat to keep it perpetually erupting. That finding alone rewired how scientists think about what makes a world geologically alive. And it meant that moons, not just planets, could be laboratories for extreme geology. But Io's volcanoes were also pointing at something bigger. If tidal heating was deforming Io, wouldn't similar forces be acting on its neighbor, Europa? Voyager's images showed Europa's surface covered in a web of cracks and smooth plains, the kind of texture you'd expect if a liquid layer beneath the ice was shifting and refreezing. It wasn't confirmation of an ocean. It was the first serious evidence. That hint launched decades of follow-up missions, including the Europa Clipper, which is currently en route to investigate whether that ocean could support life. Saturn brought a different kind of surprise. The rings, which astronomers had observed for centuries as smooth, elegant bands, turned out to be anything but. Up close, Voyager revealed them as billions of individual particles, chunks of ice and rock, some the size of a house, some the size of a grain of sand, organized into thousands of distinct ringlets with gaps, waves, and spiral structures carved by the gravity of nearby moons. They weren't solid. They were a dynamic, constantly shifting system. And then there was Titan, a moon wrapped in a thick nitrogen atmosphere so dense that Voyager's cameras couldn't see the surface through it. A moon with weather. That detail would drive scientists to send the Cassini-Huygens probe specifically to crack it open decades later. Because an atmosphere meant the possibility of chemistry, and chemistry meant the possibility of complexity. Then came Uranus, and here the script flipped entirely. Voyager 2's 1986 flyby revealed a bland, bluish atmosphere, but also an unexpectedly tilted and offset magnetic field, and provided the first detailed images of its dark, faint ring system. Its instruments measured Uranus's magnetic field and found it tilted at a bizarre angle of 59 degrees, relative to its axis of rotation. A highly unusual geometry not seen at Jupiter or Saturn. Scientists still have no definite answers, but the tilt suggests flows deep in the planet's interior, and it remains poorly understood. And whether it is connected to the extreme tilt of Uranus's rotational axis is one of the central open questions in planetary science. 40 years later, that magnetic field is still not fully explained, meaning Uranus remains one of the solar system's most enigmatic worlds. Neptune was last, and it saved the most dramatic moment for the end. The winds there clock in as the fastest in the solar system. On a planet with no solid surface to slow them down, they just keep accelerating. Neptune lacks a surface entirely, so there are no mountains or valleys to slow the wind down. And exactly how those winds reach such extremes remains unknown. But the real revelation was Triton. Its retrograde orbit, circling Neptune backwards, indicated it was almost certainly a captured Kuiper Belt object, evidence of Neptune's violent past. Voyager 2 images showed active geyser-like eruptions spewing nitrogen gas and dark dust particles several kilometers into the thin atmosphere above its surface, a moon that shouldn't be there, orbiting the wrong way, with geysers still firing. Triton's remarkably young, sparsely cratered surface indicated active geologic processes, with fractures, ridges, and nitrogen geysers that hinted at a possible subsurface ocean, meaning even at the edge of the solar system, worlds were still alive. 4 planets, 4 encounters, and every single one of them shattered a prior assumption. Only Voyager 2 continued onward to Uranus and Neptune, making it the sole spacecraft ever to study the ice giants up close, meaning everything we know about those 2 worlds still comes from a single flyby, decades ago. After Neptune, both probes kept going. The solar system, it turned out, didn't end where anyone thought it did. Of all those planetary stops, which discovery hits hardest for you? Io's volcanoes proving moons can be geologically alive, or Triton orbiting Neptune backwards like it was never supposed to be there? Drop your answer in the comments below, because the planets were just the warm-up. What happened when both probes finally crossed into interstellar space is where things get genuinely strange. Voyager 1 crossed the heliopause, the boundary where the sun's wind stops pushing outward, in August 2012. Heading in a different direction, Voyager 2 crossed a different part of that same boundary in November 2018. 6 years apart, 2 different trajectories, and what they found when they compared notes rewrote the model entirely. Scientists had always assumed the heliosphere, the sun's giant protective bubble, was roughly symmetrical, a sphere, more or less, expanding evenly in all directions. The 2 probes detected different structures. Voyager 1 found a stagnation region, where the solar wind slowed to 0 before reaching the heliopause, whereas Voyager 2 did not. Voyager 2, on the other hand, discovered the solar bubble can be leaky, with solar plasma escaping past the heliopause into interstellar space, a finding confirmed across multiple published studies. Same boundary, different physics. The heliosphere isn't a perfect sphere. It's asymmetric, compressed, and irregular in ways the textbook models completely fail to predict. And then there was the plasma. Immediately outside the heliopause, the interstellar plasma was hotter than expected, running at roughly 30,000 to 50,000 Kelvin instead of the predicted values. The density was off too, far higher than models anticipated. And the magnetic field direction? The magnetic field beyond the heliosphere was expected to point in a different direction and failed to do so. The models weren't slightly wrong. They were structurally wrong. Everything we thought we knew about the boundary between our solar system and the galaxy had to be rebuilt from scratch, using data from 2 spacecraft running on 1970s hardware. Which brings you to where we are right now, in 2026. This is where the story stops being historical and starts being urgent. On April 17th, 2026, engineers at NASA's Jet Propulsion Laboratory sent commands to shut down an instrument aboard Voyager 1 called the Low Energy Charged Particles Experiment. The nuclear-powered spacecraft is running low on power, and turning off the LECP was considered the best way to keep humanity's first interstellar explorer going. That instrument had been running almost without interruption since 1977, nearly 49 years of continuous operation. Each Voyager originally carried 10 sets of instruments, and 7 have already been turned off. The probes are being slowly, deliberately dismantled in space, one piece at a time, to keep the last few instruments alive just a little longer. Both probes rely on a radioisotope thermoelectric generator, a device that converts heat from decaying plutonium into electricity. Both probes lose about 4 watts of power each year. After almost a half century in space, power margins have grown razor thin. 4 watts per year doesn't sound like much until you realize the engineers are now making decisions about which half-watt motor to leave spinning and which one to kill. The team is working to finalize a more ambitious energy-saving fix they call the Big Bang, designed to swap out a group of power devices all at once, turning some things off and replacing them with lower power alternatives to keep the spacecraft warm enough to continue gathering science data. With the current power conservation plan in place, engineers believe the 2 probes could have enough electricity to continue operating with at least one science instrument into the 2030s. But eventually the power dies, the signal goes quiet. And here's what that actually means. Voyager 1 is expected to reach the theorized Oort cloud in about 300 years and will take roughly 30,000 years to pass through it. In about 40,000 years, it will pass within 1.6 light years of the star Gliese 445. The golden record aboard each probe, carrying sounds, music, and greetings from Earth, will keep traveling long after every instrument has gone dark, long after every engineer who built these spacecraft is gone, long after the civilization that launched them has changed beyond recognition. When the power finally dies, Voyager doesn't stop. It just stops talking. And it becomes humanity's longest-lasting artifact, 2 small objects from the 8-track era drifting through the galaxy for billions of years, still carrying the sound of Earth. Subscribe if you want more like this, and watch the next one on screen right now.